September 2019, and the poster has been on my door since then. And it's great to be here at this thing. It's really true. It's really true. Yeah. I can't see my slides from here, so I'm going to go over there. Okay, so I'll talk about some recent progress and challenges for direct detection of light dark matter. And so I'll start with an overview talk. Some of you are experts, some of you probably know about the topic, but are not working on it directly. So I'll give an overview talk. It's very informal, I think, supposed to be, so let's just have questions throughout. And if I don't get through my talk, that's totally fine. Okay. So here's the outline. I'll start with some overview and some recent progress, just highlighting some things that I think are important. It's impossible to cover everything. Then I'll talk about sources of low energy backgrounds. I'll explain why I think this is an important topic to think about. And think about new signals, so I'll discuss diurnal modulation, which is not a new signal people have thought about in the past, but it's a new thing for sub-GeV dark matter. And we'll look at how it's important. I'll briefly mention new detection concepts, which is also collaboration with people who are at the workshop. So just very briefly, to maybe start some discussion down the road for later this week. And if there's time, I'll discuss calibrating the Migdal effect with neutrons. Okay. So lots of stuff to cover. Let's start. And so this recent progress also I want to include a little bit an update on the sensor experiment. Okay. And just interrupt with questions, please. So to set the stage, so WIMPs, weakly interacting massive particles, so they lie at a GeV and above. And there's tons of progress over the past few decades on looking for them. And what I'll focus on here is lighter dark matter. So in general, you need a hidden sector for this. Some hidden sector where dark matter interacts with some new particles, some new forces around. In general, for direct detection, down to the keV scale, we can think of dark matter scattering. So the kinetic energy of a keV dark matter particle is about a millieV. That's the lowest energy that you can excite something in a system, like in a phonon or so. So we can think of scattering. And you need to probe, in principle, both nuclear and electron interactions. There can be different mediators that leave different signals in your detector. So you sort of need lots of different approaches. And there's lots of models where people have figured out concrete production scenarios that are not just thermal freeze out, but freeze in. There's the strong interacting massive particle, the SIMP mechanism, ELDR, co-annihilation, and here's just a short collection of some references. Now below this mass, you can still probe dark matter essentially with the same kind of systems where we think about dark matter absorption. So in this case, the dark matter has to be bosonic. It has to be bosonic below keV for several reasons, but also for direct detection. You can think of it, if it's a boson, it can be absorbed by a standard model particle, like an electron in particular, and it can absorb the whole mass energy. So again, we can go down to millieV, because for a millieV particle, if you absorb it, you can get at least a phonon or something like that in your system, excite something. Okay. Now, there's been a lot of progress in probing light dark matter over the past 10 years or so. So we now have a lot of different detection concepts that use a variety of target materials. They all try to tease out some kind of signal in some target material. Some of the target materials are quite exotic. They're also very of interest to condensed matter people, theorists and experimentalists. And there's a nice connection with condensed matter physics. We've had improved calculations of dark matter scattering in a crystal. It's actually a non-trivial problem, and there's been a lot of progress on that. And then a bit later on, I'll also talk about there's an improved understanding of low energy backgrounds. So when we talk about backgrounds, you might think, isn't that an experimentalist job? But actually, there's a lot of novel backgrounds that come up that people haven't really thought about in the context of light dark matter. Because basically, you're looking for tiny, tiny signals, and anything that can cause a tiny signal. It's not going to be the same kind of backgrounds that people are used to for WIMP searches, where you look for more keV energy signals. We look for EV and eventually down to millieV backgrounds. So I'll start with that, then I'll talk about the experimental progress as well. So there's many detection concepts. I don't want to discuss them. I just want to flash some plots that collaborators and I made for a white paper that was written in 2018 for the Department of Energy, US Department of Energy. So there's basically the cross-section for dark matter scale of nucleus as a function of the dark matter mass. This is a GeV, so we're looking at below a GeV scale here. Back then, these were the existing direct detection constraints. You can see this was for the Department of Energy, so there's some key milestone or some political speak. So this is basically a collection of models where you can get a SIMP or an ELDR or freeze out, different various production mechanisms that people have identified. And then there's lots of target materials here where people try to have proposed ideas for detecting dark matter that's very light. So molecules, semiconductors, superfluid helium, polar materials. We can do this for a heavy mediator. We can do this for a light mediator, where the constraints are a little bit different. Semi-metal superconductors that people have proposed. So lots of ideas, and this keeps flashing. I don't know, but anyway, nothing I can do about it. And then the bosonic for absorption, we can think of dark photon absorption, for example, where here goes down to 10 milli-eV. And again, we've got lots of ideas where there's a few constraints, right, sort of at high mass, high cross-section, and the idea is to probe lower masses and also lower cross-sections. So a lot of ideas, a lot of progress. The trick is to try and turn these into reality, and that is much harder than just proposing an idea. I think right now the two main basic concepts, direct detection concepts that are being used or have been used already by experimentalists to probe dark matter below a GeV scale are dark matter electron scattering and dark matter nucleus scattering with the Migdal effect. So the idea is that dark matter can scatter over an electron, a bound electron. Here I've drawn it like an atomic system, but you can think of also a semiconductor, for example, where there's some valence band that's filled with electrons, and then there's a little bit of a gap, a band gap, and then you get to the conduction band, and you can excite the electron across the band gap to the conduction band. And the idea is to look for this little bit of ionization that you might get from an electron recoil, okay? The nuclear interactions you can also probe with something called the Migdal effect. So the idea there is that the dark matter hits the nucleus, and as the nucleus recoils, the electron cloud takes some time to catch up, and there's some chance of ionizing the atom. And again, you can also do this in a semiconductor or in other systems. And I think these two ideas, with noble liquids in particular as targets, and semiconductors, there's a few other examples as well, but those have been used mainly to probe down to GeV scale at this stage. But as you saw, there's lots of other ideas out there. Now, the reason these work well is that you can transfer an order 1 amount of the dark matter kinetic energy. So again, the kinetic energy of the dark matter is a half mv squared, of course. V is about 10 to the minus 3, or if we take the maximum velocity of the dark matter in the galaxy, about 2 times 10 to the minus 3. And if you put in the numbers, the kinetic energy is about an EV for a dark matter mass of 500 keV. So if you have a semiconductor like silicon, the band gap is about an EV. In that case, you can, in principle, dark matter as light as 500 keV can excite that electron across the band gap. Okay. And this is a very different, so the fact that you can transfer an order 1 amount of the kinetic energy is very different from dark matter scattering elasticity of a nucleus, which is the standard WIMP probe. Okay, so you sort of need to find interactions that allow you to really extract more of the kinetic energy of the dark matter than you would just get in an elastic nucleus scattering, which is the standard WIMP search. So the typical signal that you get here is you get one or a few electrons, okay, in both of these cases. So you can get, clearly you can see from this picture you get one electron, but this electron could have a little bit of kinetic energy and excite other atoms around it, or in a conduction band. Once it gets to conduction band in a semiconductor, you can also excite additional electron pairs. So you can look for, sometimes you can get several electrons from this. So it's one or a few electrons that you want to, one to a few electrons that you want to look for. Same thing with the Migdal effect. Okay, the excited electron can excite additional electrons with it. So here's a plot of the spectrum that you get of electrons as produced by dark matter scattering. So here's an example, it doesn't matter that much, but it's 10 MeV, some cross-section, doesn't matter exactly what the cross-section is, but you see events as a function of the number of electron hole pairs being produced in silicon, and you see the steeply falling spectrum. Okay, so you really see that the spectrum that you get of electron being produced is very small. It peaks at the low end. So you really want to probe very, very low number of electrons to get the maximum cross-section sensitivity, maximum sensitivity. Here's a plot for dark matter nucleus scattering emitting with the Migdal effect. We're emitting an electron as well, and that electron can ionize additional electrons. So you get again the spectrum that peaks towards the low end. So in both cases, we have the sharply rising spectrum towards the low energies, and you really need the single or few electron sensitivity to capture more potential dark matter events. Okay. Yeah. Right. Yeah, so depending on the experiment, they may not have sensitivity to single electrons, but they might have sensitivity to 5 electrons, and then you just will miss out on a good part of the dark matter signal. But that really tells you that you get a qualitative change if you lower the threshold, right? If you lower the sensitivity, if you increase the sensitivity of experiment, you really gain a lot, okay? If you can do it. Of course, if you, yeah, so it's whatever you can do. Now, there's been a lot of progress in calculating these scattering rates. This is from a plot from a paper that we had in 2015. So why is it non-trivial? Well, the electrons in a semiconductor, in silicon, for example, they are part of a many-body interacting system. We need to describe those wave functions very accurately in order to understand exactly what the momentum distribution is, in order to understand exactly how the dark matter can scatter off the electrons and then excite it. It's not just like WIMP scattering, dark matter nucleus scattering, where you've got essentially billiard ball scattering, which is very simple to calculate. Even there are subtleties with the nuclear form factors and so on, but it's a much harder problem for electron scattering. And there have been several theory groups that have been working on this, and they've written the scattering rate in different ways using the electron loss function, which in principle which can be measured. They've included all the electrons, not just the valence electrons, and looked at various kinds of dark matter interactions. So there's been a lot of progress, and just some work in progress from my own group at Stony Brook. So this is being led by a student, Aman Singhal. So that poor guy has 3 advisors, so myself and 2 serious people, 2 condensed matter theorists, Cyrus Dreyer and Maria Fernandez Serra. And there we were looking at the theory uncertainties inherent in trying to calculate these scattering rates. And we looked at changing the different basis sets for how the electrons are described. Again, here's the spectrum as a function of the charge being produced. And we have different basis sets. So just seeing how the description of the electrons, how that affects the spectrum being produced. And you see some uncertainty as you change this basis set, but thankfully it's not that big, and we have different exchange and correlation functionals, so how the electrons are interacting in that system. That also you use condensed matter tools essentially to calculate these kind of functionals, and then you have different functionals available that you can use in your dark matter electron scattering calculation. Again, the uncertainty is not that bad, and then also checking some numerical uncertainty. So big picture wise, the theory uncertainties are not 0, but they are under control, which is nice, okay? And theory, yeah, we can talk more about this. And this is something that I think is important. It's a non-trivial calculation, but it seems to be working well. And there's several groups now that are getting consistent results. Okay, so I've talked a little about the theory progress. I'll talk about the third point in theory that I had listed on the phenomenology backgrounds in a few minutes. There's also multiple experiments that can now probe these small signals, right? So getting back to the question that you had, which experiments, what's the sensitivity actually of experiments, and can you actually reach the single electron threshold? So there's actually several instruments now that can see even single electron excitations. So examples are xenon, argon, two-phase TBC, so dark side, which I think we'll hear about more later this week, and xenon, the various xenon variations, and LZ. Then there's also phonon or heat sensors, which use, for example, transition net sensors, which can detect single electrons as well, and then also skipper CCDs that we use, for example, in Sensei, and that DAMEG-M is using, and then we plan to use for an experiment called the Skura, which I'll also tell you about a little bit more. So just to basically, so this experimental progress, so these detectors that I just mentioned, they've basically allowed us to go from a situation in 2012 where we had one limit on dark matter electron scattering as a function of the dark matter mass. So here's the mass up to GeV. Here's the dark matter electron scattering cross-section. 2012, we had one limit from old data that was taken by Xenon 10 in, I think, 2006 or 7 or so. And now we have this plot with a dozen lines essentially filled in using noble liquids, using silicon, using germanium, using EJ301. That's something that Carlos and Ben can tell you more about, using a molecular scintillator where they were looking for dark matter electron scattering that then produces photons using PMTs, so they can tell you more about this. So there's lots of progress and a lot of interest from experimentalists. Again, we can make this for different mediators. So for light mediators, the cross-section actually increases as the 1 over q to the 4, so it increases for lower momenta, and in which case, a lower threshold, any experiment that has even lower thresholds will be greatly enhanced in sensitivity. Okay, so if you go back one here, Sensei, which I'll tell you about in a few minutes, has currently the strongest constraint down at the low mass end, but at higher masses, xenon 1 ton has a very nice analysis where they have the strongest constraint on dark matter Edgerton scattering with a heavy mediator. But once the cross-section is mediated, once the interaction is mediated by a light mediator, the cross-section has this 1 over q to the 4 enhancement, and the lower threshold detector, like Sensor, currently dominates that search. Okay. But this might change in a few weeks. Who knows? So there's lots of activity in the field where people are looking for this. Yeah, and here, for example, is the effect of the impact of the Migdal effect. So here's now the dark matter nucleon cross-section as a function of the dark matter mass, again, focusing on just below the GeV scale here. This is looking for elastic dark matter nucleus scattering, so the usual WIMP thing, WIMP interaction. But now if you include the Migdal effect, where you get these ionization electrons, and you use the same detectors to look for the ionization signal, now suddenly you can really probe much, much lower masses. And you see various attempts to try and do that from various experiments that are sensitive to the same thing, again, looking for small ionization signals. So this theory progress, realizing that the Migdal effect is actually something, it's been around for a long time actually, but more recently it's been realized that it's actually a very important signal to look for. That's had a big impact in looking for these type of interactions for light dark matter. Very quickly, how do these experiments work? So schematically, so these two-phase TPCs that xenon, 10, 100, 1 ton, etc. are using, or dark side are using, they essentially have a liquid xenon or liquid argon target. There is a gas phase above this target, and then photomultiplier tubes which detect photons. And the idea is that when the dark matter comes in, creates an electron here or a few electrons, those electrons will drift up under the electric field that's applied and then get extracted into the gas phase. In the gas phase, they bounce around against the xenon atoms, they excite them, those de-excite and emit light that are affected by the PMTs. And it's pretty easy for these experiments, like dark side or xenon, the 10, 100, 1 ton, to see single electrons. The problem is they see a lot of them, and there's some background that's not under control at this stage. Okay. But in terms of just seeing a signal, is pretty easy for these experiments to do that. Phonon sensors, so for example, you can use calorimeters like a transition net sensor essentially, where you've got some silicon or germanium target and you apply an electric field across it. And when the dark matter comes in, again creates some charge, some electrons, then those electrons will drift in that field. So you actually create electrons and holes. Okay, so when you excite an electron from the valence to the induction band, you create an electron hole pair. And you can create a couple of electron hole pairs, and those will drift under the electric field and emit phonons. And those phonons will get detected by the transition net sensor. And again, they've achieved, so super CDMS, for example, and Edelweiss, they've achieved single electron sensitivity. Okay. So then let me talk about Sensei. So Sensei doesn't use transition net sensors or, well, the things I've talked about before. In Sensei, we use something called skipper CCDs. So you have a silicon CCD, which consists of order 1,000 pixels. The idea is that the dark matter will come in, create an electron, hit an electron in the valence band, excite the electron to the induction band. Maybe that excited electron is going to create additional electron pairs, so you might get a few electrons from this. And then in this material here, these electron pairs, there's electric field across it. Those will drift to opposite corners. And then once they get there, they get held, and then they get eventually read out. So here's a picture of one of the CCDs that we have used in Sensei. Just to give you an idea of scale, so, well, in the US, this is a dime, so it's a pretty small thing. So these things are pretty small, right? 2 centimeter by 10 centimeter. There's about 5.4 million pixels here, and thickness is about 675 micrometers. And the idea is that what we can do is we can divide this CCD into 4 different parts, 4 quadrants. And in the corners are things where you can read out the charge. So the basic idea is that the charge gets created in these pixels, as you expose a CCD, you create some charge, hopefully from dark matter, in those pixels, and then you shift the charge to one of these corners. And in one of those corners, so you shift the charge into these corners, into something that we call the serial register, and then the charge eventually makes it into this readout stage. And what you can think of is that you have a little capacitor there where you put the charge on and you measure a voltage. And the thing, so an ordinary CCD does that very easily, has done it for many, many, many years. The skipper CCD, what it does, is able to read the same charge package multiple times by just shifting it back and forth, and each time taking a measurement of the voltage and getting an estimate of how much charge is sitting there. And you do that 100 times, you can do that 1,000 times, and then take the average, and you can get a very good idea of how much charge is actually inside that particular pixel. Okay. So you just shift it back and forth multiple times, and this allows you to get readout noise where you can measure exactly how much charge is in these pixels. Okay. So this was demonstrated in 2017, led by work by Javier Tiffenberg at Fermilab. And this now allows you to also look for dark matter. So you just take lots of CCDs in principle and expose them, and hopefully just see dark matter. So to read the entire CCD takes a few hours if you want to get single electron sensitivity. That's one disadvantage. It takes a long time to read out. I mean, one of these shifts is very quick. That's 10 milliseconds or so. So we can run the CCD differently. So what we've done in the past, we've exposed the CCD for a day and then read out, and the readout takes like 6 hours or so by sampling 300 times each pixel, each pixel to get sub-electron resolution. So it's like a day exposure. Okay. So I'll talk about backgrounds. Yeah, I'll talk about backgrounds actually in a few minutes. Okay. Okay. That's a very good question. That's the thing people think most of the time about, like what is backgrounds? What is backgrounds? Yeah, I'll talk about that. Okay. So we have a collaboration. It's been growing steadily. This is a very old picture, but anyway, there's basically just a few institutions. So Tianjin will also be here. Oh, this I can't see anything. Tianjin will be here soon this week. We have a group at Stony Brook. Fermilab is the lead institution in terms of the technical stuff, making these things work. Tel Aviv is involved. And Snow Lab, this experiment will eventually is situated already at Snow Lab. We have a detector operating. And so we've actually got two detector systems operating, one at Fermilab near the Minos hole where they look for neutrinos. Sometimes I say Sensei at Minos, but it's nothing to do with neutrinos. It's sitting near the Minos hole where we have a little detector operating. This is a picture of the detector, what it looks like. The CCD is sitting in this vessel there. And it's about 100 meters underground to reduce the background from muons that will go through the CCD. And there's a little bit of extra lead shielding to reduce the radiation as well. So that's one detector system. And with that one, we've been able to achieve, over the last few years, 3 different science results. So one in 2018, one in 2019, one in 2020. Here's the limits. So this is the best one we have right now in 2020, which sets the strongest constraint across the wide mass range on dark matter Henderson scattering for a light mediator. This line here, along this line, you can get the right relic abundance from dark matter Friesen, just assuming a simple dark photon mediator. In the early universe, the standard model particles can annihilate and produce the dark matter. So the dark matter is non-thermal equilibrium. The interaction is so small that you don't get thermal equilibrium, but you can slowly freeze in an abundance with this mechanism. And that's where you want to lie, and we're getting slowly closer to that. Okay. Yes, so in this case, I'm assuming there's a dark photon with some kinetic mixing parameter and some interaction with the dark matter particles, some alpha dark. Yeah. Yeah, alpha dark epsilon squared is 10 to minus 10, I think. It's an existing model. Well, yeah, it's a model, yeah. So you have a dark matter interacting with a dark U1, which is kinetically mixed, yeah. Yeah, so this is a nice little target, which also allows you to go to below a GeV, below the MeV scale. Say again? It also works for what? Yeah. Yeah. But this is a concrete model where you can get the right radical abundance. So along this line, you get the right radical abundance. Below it and above it, you don't. Okay. Below it, you get too little in this case, and above it, you get too much. Above the line, you overproduce in this model. So it's along the line, yeah. It's really along the line in this particular model, yeah. As an example model. Yeah. Okay. So at Snow Lab, we also have something operating. So this is much deeper underground in a mine there. Here's some pictures before the thing was put together. And this is the lead shielding being built up. And eventually, this is what it looks like. Nicely encased in some lead shielding. And right now, we've got a system operating that's of order 10-ish gram or so. The goal is to build it up to 100 gram later this year. But also before doing that, to really understand the data that we're getting. We're trying to reduce the backgrounds and understand them. So that's sort of the status right now. And then the idea is that hopefully we can probe well below this line. So this is the projection for 100 gram year operation. Okay, so well below this, even if we don't get that right, you'll still be well below the freezing line for a wide mass range. And then there's plans. So already Damic M has a detector. They want to get to 1 kilograms of skipper CCDs. They already are also taking the first data at Modane in France, an underground mine there. Their goal is to build up to 1 kilogram and get this one. And then in the US, there's an experiment called Oscura, which is hoping to do a 10 kilogram version of this. And the R&D for that is funded by the Department of Energy at the moment. And if that goes well, in principle, there'll be actual funding for the experiment in a few years' time. So there's really a lot of progress, right? I mean, I showed you 2012, there was just one limit, and now there's a lot of interest. And not just Sensei, I focus on that because I'm involved in that, but dark side and xenon and lots of other ideas that are coming up. Okay. So as far as I know, well, okay, so I can show I have some backup slides where we looked at magnetic dipole moment or electric dipole moment interactions where dark matter can get the right radical abundance from freezing. Those tend to be lower. And I'm just showing here for this particular, for the light mediator case, the line, there's also projections for heavy mediator where you've got a strong interacting massive particle or an elder, those different kinds of ideas that people have talked about. So if you want, I've got some backup slides as well. But there's different kinds of models where you would want to go lower in cross-section. Not necessarily on this parameter space, because this is for the freezing line with the light mediator specifically, but on other parameter spaces, yeah. Yeah. Well, for this particular model, you will just don't have enough dark matter. But in other models, you can, yeah. Right. Well, no, so this is just because you want to get the right radical abundance for this line. But there's other models where you wouldn't want to really probe the full 10 kilogram year exposure. The other thing to say is that 10 kilogram year is a good number to keep in mind because at that point, solar neutrinos scattering coherently of your nuclei in the silicon can produce low ionization signals as well. And they become a real problem for for silicon at the scale of 10 kilogram year exposure. So where it's hard to distinguish from solar neutrinos. And then to go beyond that in exposure is going to be difficult. Yeah, okay. Projections for some other models in backup. Good. Okay. All right, so we talked about lots of progress. I think there's also significant challenges ahead for low mass direct detection. And a lot remains to be done. And I've just given you a list with some random order. I'll talk about some of these depending on time, how much time we have in the talk today. I'll talk about some of these a bit more, but I think what's important is to really understand and mitigate low energy backgrounds. So people know about radioactive backgrounds like Compton scattering and so on, but there's new detector effects that are coming in or new kinds of ways of generating low energy backgrounds that are important, and we haven't understood most of them yet, I think. And I'll talk more about this. So I'll talk about some progress for at least understanding sense with the CMS data. Then I'm saying some things are very obvious what I'm saying, right? But I think we need to develop new signals for dark matter, and theorists, of course, have been great at doing this. So theorists have, for example, said that the dark matter that is very light can scatter in the sun and then gets heated up, and then even very low mass dark matter can get heated up and then make it to your detector, and you can probe your dark matter that's well below an MeV, well below an keV with that. It's at a reduced cross section because the flux of dark matter coming from the sun after it's being heated up will be not much, but it's a new signal. And here I'll talk about diurnal modulation. I think even though there's lots of detection concepts that already exist, there's room for more, because right now those detection concepts that I showed you at the beginning, right, with all these projections, they're just made up, frankly, right? They're just not based on necessarily, they're just based on a rate calculation of a signal, of a scattering rate for dark matter interacting with the system. Great, but you actually have to build it, you have to control the backgrounds, you have to expose it, and that's not trivial. And thinking about new detection concepts that might have complementary challenges is, I think, still useful. And I'll talk about two ideas, one on quantum dots and doped semiconductors, very briefly, just 2 slides on each, if I get to it. You could capture it. No, I think you can capture it, yeah. Yeah. Oh. Yeah, that might be true. No, but what I'm saying is not capturing. What I'm saying is scattering in the sun and heating up, actually increasing its velocity, and then coming back to the Earth. And this is an idea by Maxime Pospelov, not mine, right, just to be clear, sorry, it's Maxime Pospelov, Timo Nemkin, Chris Kovaris, Josef Pradler, and Haipeng An, I think, were the first ones to propose it, yeah. Yeah, it's not capturing it, yeah. Yeah. Another idea is cosmic rays that interact with the dark matter and upscatter it. So again, lots of people have talked about it over the past few years. So those are cool signals because it really allows you to go lower in mass. It's very high cross sections, right? Because you have a small flux of this, but still, yeah. Right, right. Again, cosmic ray, not my idea. I think Maxime and various people have worked on this. Okay, so yeah, I'll talk about this. And the fourth thing I'll mention of time is that there's a lot of signals and also backgrounds that we're talking about which haven't been calibrated at the low energies that we care about. So for example, the Migdal effect, never been measured, never been observed in the lab, not been calibrated. We make these limits, we don't know if they're real. Okay, we have to actually see this with neutrons. And I think this is another important thing. Compton spectrum, how difficult can it be, right? You just calculate it. But actually, it's not that trivial. You have to, again, take account of the band structure effects in silicon, for example, to really calculate the Compton spectrum accurately. And that's something that we're doing right now to understand what is the shape of the Compton spectrum at the lowest energies where these experiments are actually looking for dark matter. That's something that needs to happen. And then you want to calibrate it again with data. Okay. So those are the kind of things that also need to happen. And I'll give one example with Migdal effect. So I'm working with with my student, my theory student, and also with some experimentalists on doing this for xenon and silicon. Okay. Yeah, that's depending on how much I get. And then your other things that we need to do, sharpen theory predictions for dark matter signals. So I mentioned that when the dark matter, for example, hits the electron, let's say in xenon, you excite the electron, you ionize the electron. But how many additional electrons do you get from that excited electron? Is it 2, 3? No one's ever measured this at these low energies. No one's ever calculated this properly at these low energies. Okay, that needs to be calculated. That's something else that needs to happen, and I won't talk about this, but yeah, we have some work in progress on that. Then something obvious, it's very easy, in quotes, to operate at 1 gram detector. It becomes harder to operate a 10-gram detector, a 100-gram detector, a kilogram detector, right? It becomes progressively harder. So this is an experimental job, of course, so just increasing the mass, and until you've actually done it, you don't know if you can do it. Right? There's lots of challenges that come in that you have maybe not have thought about. And then, of course, we've gone down to EV scale thresholds with silicon detectors. We want to go lower. to even lower thresholds, and really have large mass detectors that can probe this. And that's, again, an experimental question. Lots of people are working on that. So that's the challenges ahead, and let's see how far I get. Okay, sources of low energy backgrounds. Okay, so here's a little thing which maybe not everyone appreciates. All sub-GeV direct detection experiments essentially are seeing excess of low energy events that they do not understand. This is slightly embarrassing maybe, but it is true. And here's, for example, just taking ionization detectors, where solid state ionization detectors, so not even xenon and dark side, which are also seeing excesses that they don't understand. Here's the rate as a function of energy deposited in electron energies, okay? And you see this nice flat spectrum, probably quantum scattering and so on, but then you see this increase in rate. Here's a zoomed in version, which just zooms in at the lowest energies. And you see all these, exponentially rising excesses. And here's Sensei, which also rises exponentially, okay? And, if the origin of these events, this is not dark matter, first of all, okay? People have tried. It's very hard to come up with a model of dark matter that explains all these excesses. I think there's multiple origins, and I think most of them, maybe some of them are dark matter, but most of them might be, will be detector effects or something, right? So if the origin of these events is not understood, just to say something obvious, right, it would severely limit the sensitivity to sub-GeV dark matter. So this is an important topic, I think, where theorists also can play a role in thinking about what kind of effects are causing these low energy events. And I'll give you one example of, so far, one successful story, partially successful, I should say. So let's focus on Sensei and super CDMS HVEV. So Sensei already mentioned. Here's the events that Sensei sees. So these are the pixels with the charge measured in these pixels. So here are all the pixels that have no charge in them. Okay, so that's just 0 events. Here are all the pixels with 1 electron in them. Here's pixels with 2 electron events in them. And because we don't have perfect resolution, so this was taken with some number of samples per pixel, we get the smearing, but essentially all these events are 1 electron events, and all these events are 2 electron events. We see a lot of them. They're not Compton scattering. They're not just some obvious background, some radioactive background. Okay, and this was a mystery for a long time. In super CDMS high voltage EV, so they apply a voltage across the detector to accelerate the electrons and measure the phonons that come from that. So in this case also, you see 2, 3, 4, 5, 6 electron events. And what these are was not obvious for a long time. And at least for now, with Daniel Gana Ugrinovich, my former student who's now at UCSD, Mukushula Purka, and Peiji Du, who is at Stony Brook still, moving to Rutgers. So we've identified a major contribution to these events, at least. I'm not going to say the whole excess, but at least a major contribution to this. So here's an image from Sensei. So we take these data images and then we read them out, and then you can look at them. So here, for example, is this little wormy thing is an electron. This is an X-ray, maybe 10 keV or so, where you get absorbed, and then the charge diffuses a little bit in the CC, so you get this little bit of a blob. Here's a muon, a nice straight track, right, a minimizing ionizing particle. But then I think you can see lots of dots all over the place, and those are the 1 electron events, okay, that we don't understand. That we've only partially understood right now, which I'll tell you about. So there's many 1 electron events. The interesting thing with the Sensei data is that what we realize is that the position of these 1 electron events on the image, they are correlated, at least partially, with high energy events. So near high energy events, you get an excess of 1 electron events. And then if you go far enough away from these high energy events, the rate seems to decrease. The rate of 1 electron event seems to decrease. And also, one thing that we did is that we changed the shield thickness of when we're taking data in the CCD, and we realized that the 1 electron event changes as you change the shield thickness. So first of all, it's not dark matter, because dark matter will not care about the shield, right? But also that gives a clue that it's environmental radiation somehow causing these 1 electron events. So what we've managed to realize is that obvious physics effect, right? You go to Jackson and you realize an obvious thing is that these radioactive backgrounds, the cosmic ray muons, they can produce actually many photons that have ordered the EV scale, which can shrink of radiation. So here, for example, is an image schematic of a detector. So you've got a detector inside some copper vessel. Here is the detector. It's being held by some holders, right? Those are not metal, these holders. There's some dielectric material usually. There's cables around. And what can happen is that the high energy charged particles, like muons, can go through the detector, and as it does, it can Cherenkov radiate. It can go through the cables, and can Cherenkov radiate. There's impurities in the holders, there's impurities in the cable. They can produce electrons that are above the Cherenkov threshold in that material and can produce photons. You can also get something called radiative recombination. So in your detector, if your detector consists of silicon, then you can create electron-hole pairs. Sometimes those can recombine to produce a photon. All these photons that you get will be of the scale of order EV. Okay, that's just because these are dielectric materials, and if you look at the dielectric function, they will be able to support radiation of Cherenkov at that scale, at the EV scale, which is exactly where it's enough then to create an electron, for example, in silicon. Yeah. Yeah. Yeah, so you can shield like crazy, but you've got some impurities around. I mean, here's the image from sensor, right? This is the stuff we see. These are all electrons. That's some radioactive background, right, despite the shield. Now, this was just 100 meters underground, not very well shielded, right? This is not in a better shield like underground. It's no lab. But it's hard to get rid of it completely, right? And the unfortunate thing also is that the photons that you get from Cherenkov radiation and this radiative recombination are of that scale. So then the idea is, if you look at the sensor detector, so here's the image of the sensor detector from the inside. The CCD is facing down. It's in some copper vessel. Here's a schematic. So there's some skipper CCD here, glued to some other piece of silicon just to hold the detector and make sure you can actually connect it to electronics and so on. And what can happen then is that a track, let's say a muon, will come through. It'll pass through the silicon in this, what we call the pitch adapter, basically just a piece of silicon holding the CCD, as I said, through the glue, which is this epoxy, and then through the CCD. It's going to produce photons that are less than 4 eV. Now, if the photon is far away from the band gap of the silicon material, it can't travel very far. It's going to get absorbed right away again, and then just create an electron hole pair very close to the track. Those are easy to get rid of because you are removing the high energy tracks anyway. If we go back to this image, we will remove all the pixels that are near these high energy tracks. We'll draw some halo around it that we're not going to look at, okay? But the problem is that sometimes you can get photons that are very close to the band gap, and those can travel a long distance. They essentially can travel along the distance of the CCD, of order the distance of the CCD. And in that case, you will, once it gets absorbed far away from the track, it's going to create an electron hole pair, okay? And that's going to be a background that looks like dark matter in principle, okay? So here, for example, is the number of photons that we get for one electron track. These are two different energies. For the electron, 250 and 500 keV. And this is a function of the distance of the photon will travel before being absorbed. And you can see that it can travel, occasionally 60 pixels or more. So far away from the high energy track. Then it will get absorbed and create an electron hole pair. So this is basically a problem. This is one of the backgrounds. Then there's also more subtle backgrounds. So on the back side of the CCD, there's actually a very thin layer of highly doped silicon. In that material, when some charged particle passes through, it's going to create electron hole pairs. But those electron hole pairs can recombine and produce a photon. And those photons, again, will be close to the band gap and can travel quite far. Okay. So you need to do a very sophisticated simulation, and Mukul in particular has been doing a great job at getting all the details right, taking account, of lots of different effects, thin film effects on the edges of the CCDs. The photons can bounce around before they get absorbed, and all kinds of things, which I'm not going to discuss, but here's a lot to take into account. And eventually what we get is we can simulate what the Cherenkov radiation will look like. So here's the sensor data. So you see these tracks with lots of dots around, which are these single electron events. In the simulation, here are simulated tracks. So all these blue things are tracks. So these are muons here. Those will be electrons and X-ray photons. And then once you add the Cherenkov radiation and the recombination, you see that the image starts looking the simulated image starts looking like the actual sensor data. Okay. So this is a real effect, which is, now that I'm telling you it, Cherenkov radiation, of course, how could you not have thought of this, right? It's a basic electromagnetism effect. But the fact that it was actually important was not realized previously. And so you see these dots, right? These are all the single electron events that you then also get that contribute to this background. So the current conclusion that we can make, we hopefully will have a paper out soon, is that the Cherenkov, first of all, dominates over the recombination, radio recombination background, but that it only contributes in order 1 to the observed events, which means that there's some other contribution. Okay. And we don't know what that is yet. So this is something that we really want to figure out in order to make progress for the dark matter search. So good news, but also not complete, right? There's more work to be done to really understand what the backgrounds are. Just very quickly for super CDMS, this is what their detector looked like. Here's an image from the detector that they used in 2020 to take data. Here's the detector, and then they hold this detector with something called, it's basically some fiber optics material, some glass-like material, printed circuit boards, PCB. So here's a schematic, here's a detector, and they've got these dielectric materials essentially that are holding the detector, and they saw a huge event rate of single electron backgrounds and 2 electron backgrounds and 3 and 4 and so on. And again, when you can just do a simple estimate of what does Cherenkov radiation do when you've got a muon or other tracks going through this printed circuit board, in this case, those photons will again bounce around the detector and eventually make it to the silicon detector. And you only need a sub% fraction of photons that are produced to make it to the detector to give the observed signal. So it's a huge number of photons that you create. But that is a very likely explanation for what they're seeing. Okay, what are the implications? So first of all, dielectric materials in experiments are common. So you've got holders, you've got cables inside it, even inside the copper vessel. So you really need to very carefully evaluate the background if you want to do a sub-GeV dark matter search, where the signal you're looking for is 1, 2, 3, 4 electrons, right? So it's important for a wide variety of experiments that have been done or are upcoming. Then also it's important for experiments that like Super CDMS Snow Lab, right? Just to make this point. So here's a detector that Super CDMS at Snow Lab uses. This is the big, one of the big flagship experiments in the US, funded by the Department of Energy. And this is a picture of the detector, and inside the copper vessel, and you see these little holders. These are something called Surlex. They hold the CCD, not CCD, sorry, they hold the detector. And it turns out there's always some radioactivity, right? No matter how well you do it, how well you clean your materials, there's some radioactive contaminants left over. And based on their own estimates, in terms of how much background there is, it turns out that this radioactive contaminant in Surlex, from the Surlex in here, will produce about 50,000 beta decays, so 50,000 electrons every year in the detector. And those can Cherenkov radiate and produce an EV signal that get absorbed and potentially look like dark matter. In this case, yeah, it's happening in these little holders, which are holding their puck, the silicon puck. Yeah, so there's lots of things you can hope to cut most of these events out. So I'm not saying they're going to see 50,000 events a year, but it's 50,000 events a year. And their background originally was very, very small. So they have to do a careful estimate of actually what the contribution is from this. Okay. And in the end, I don't know how important it is. That's going to help. Yeah, there's lots of cuts. So a lot of these events will be cut, but at the end, I don't know how much, because you have 50,000 that you need to get rid of, right? And a lot of them will be easily cut, but the question is, are you going to cut 45,000 of them, or 49,500, or what are you going to cut? You need to cut most of them. Okay, now one fun little speculative thing is that there's of course a lot of interest in building quantum computers and using superconducting qubits. They have a coherence time, and you want that to be as long as possible. What people have found is that the coherence time of superconducting qubits is correlated with the background radiation. with the level of background radiation. And the higher the radiation, the lower the coherence time. So the effects that I'm talking about, where you produce these Cherenkov radiation, or you can produce phonons in other ways also that then limit the coherence time, those kind of backgrounds could be important. So what we learn in direct detection might actually be beneficial also for the superconducting qubit technology and increasing the coherence time. Now, fortunately, there's of course many ways to mitigate these backgrounds, but it's not trivial, and also to simulate them is not trivial. And one obvious thing is that just shield material much better, because if you shield it much better, then you also have less radioactive backgrounds, and you then don't have to, you will not have as much Cherenkov radiation being produced. But as I was mentioning with the super CMS, right, this is a very well shielded experiment, but even these tiny little contaminants can still potentially cause a problem. Okay. And there's other experiments that have other excesses which are not explained by this. Okay, so there's lots of work, I think, to be done by both, certainly by experimentalists, but also by theorists to try and understand some of these backgrounds. Okay, I can do one more topic and then stop, whatever you want. Okay, I think we started maybe a little bit late, but whatever you want, right? Okay. Okay. Okay, so let me talk about diurnal modulation. Yes. Yeah. Yeah, so they're not necessarily peak around EV, but they have support below a few EV often, okay? But it's true you can try and find materials that have different gaps, of course, as part of your holders, in which case they'll mostly emit maybe, let's say 4 EV photons, but then you detect a silicon where 4 EV photons are not going to travel very far. It's only going to travel far if it's an EV. And then if you have some fiducialization, then you can easily get rid of that background. Yeah, so there's definitely things you can think about. And just reduce the amount of dielectric holders, right? Make it, metallize them somehow, right? Maybe cover them with some metal, but still, make sure they do their job and so on. So yeah, but that's what you need to think about. And not just for the electron ionization searches, but also for phonon searches, because the Cherenkov radiation actually also will emit below the EV, below the band gap. And when it gets absorbed, it can create a phonon signal as well. So it'll also be important for people looking for phonon signals for sub-MeV dark matter. Okay. Okay, so let me talk about diurnal modulation briefly. This will be briefer, maybe. Okay. So, well known, dark matter can of course scatter in the Earth before reaching the detector. So here's a simulation that Timon made. Right, dark matter particle comes in, I guess from here, or maybe from there. And then it bounces around the Earth, scatters multiple times. It's going to change the energy of the dark matter. It's going to affect the velocity distribution. Eventually reach the detector, which in this case was somewhere in Australia. Okay. And this, of course, needs to be taken into account and is an old topic. It also gives you potentially a nice signal. So we have the dark matter wind coming from a particular direction, and we've got the Earth spinning in some angle with respect to the dark matter wind. And what we can do is we can calculate how deep is a laboratory in the Earth's shadow, right? So we've got let's say we've got the laboratory sitting here. It's got some angle theta with respect to the dark matter wind. And you can calculate what that angle is. And if the dark matter wind is directly above you, this angle will be theta equal to 0. And if you're exactly opposite, the laboratory is exactly opposite the dark matter wind, then theta is equal to 180 degrees and you're in the shadow. So if you directly in the dark matter wind, where there's very little Earth crust in the way to the wind, then there's not going to be much scattering and you're going to see a large signal. Whereas if you're in the opposite side, if the dark matter attacks on the Earth, there could be a shadow, right? You'll see a reduced section, see a reduced rate, and it could even be that you see nothing because the Earth is going to stop the whole wind, essentially, okay, if the cross-section is large enough. So it depends on the model, it depends on the cross-section, et cetera, right? And this is an effect that was discussed a long time ago by Juan Coya and Avinon in 1990s. And what the question now is that we want to answer is, how important is this for sub-GeV dark matter searches that people are doing right now? Yeah, so you're thinking about WIMPs, where the cross-section sensitivity is amazing, where they will really only interact once in your detector. Exactly. But this is not WIMP searches. So what we're talking about here is a region parameter space which is not very well constrained yet. And the kinds of cross-section we can probe right now in Sensei or DarkSide for low-mass dark matter are much, much higher, and they're not as well constrained. And for those cross-sections, you can actually get multiple interactions, as I'll show you. So you have the idea of WIMP in mind, where indeed it's going to interact once in your detector, hopefully, and never again, right, in the Earth. But this is the situation where we're not in that situation yet for sub-GeV dark matter searches. Yeah. Okay, good. Thanks for the question. Yeah, good. So we can consider two locations, for example, for a dark matter detector, right? So we can think of Sensei at Fermilab, which is 4 degrees latitude, plus 4 degrees latitude. Here's the ISO angle as a function of day, as a function of time in the day. And you see that we're sort of between, I don't know, 10-ish, whatever degrees, up to 9 degrees, which if I go back to this picture, 10 to 9 degrees, right? So you're actually seeing a lot of the wind, and you never go that far away from being not in the wind, like maybe at a 9-degree angle. You can think of a detector in the southern hemisphere. In this particular case, there's an effort in Argentina, in Bariloche, where they want to use skipper CCDs to essentially have a sensor-like experiment there as well. They are sitting at minus 4 degrees latitude, and their ISO angle is much higher, so between 90 and 180 roughly. And they will actually be sitting then in this, on the backside in the shadow. Okay. And what that tells you is that you could see different kinds of modulation in the day, right? So as the day goes on, you will of course see this modulation. The shadow of the Earth with respect to the wind is going to change as the day continues. So there's more stopping at Bariloche than, for example, a detector that's sitting at Fermilab. But having, of course, a modulation that you might be able to see in both places would be a great thing, would be very striking. So this is a way of trying to look for dark matter where despite having a large one-dimensional background, you can still look for dark matter by looking for the modulation signal. Okay. So let's ask the question now, well, how important is this signal for current experiments, right? So this goes back to the question, like what you asked, right? How often does it actually dark matter will scatter? So let's take a very popular model, dark matter interacting with a dark photon. There's a hierarchy actually between nuclear and electron scattering. So just from the cross-section, the dark photon couples the charge. So the cross-section is going to scale roughly like this. And what's going to happen is that the dark matter will, depending on its mass, but let's take a 10, 100 MeV dark matter particle, depending on its mass, is going to interact mostly with protons, with the nuclei in the Earth, and then eventually it's going to scatter multiple times and eventually make it to your sensor detector or something like that, and then hit an electron and leave a signal. Okay? And here's the mean free path for doing this. So here's the cross-section for dark matter scattering of electrons as a function of the dark matter mass. Here's a GeV, here's an MEV. Here's the sensor limit on the imprinted on the background, and these lines are the mean free path in terms of the Earth radius. So just to highlight one, this is one scattering along this line. If you go up in this direction, you will scatter, you're more likely to scatter. The cross-section is higher, you're more likely to scatter multiple times. If you go down, you will scatter less. So you see that in terms of what experiments are currently probing, at least the low masses, we're sort of sitting around the region where you expect of order 1 interaction in the Earth. Okay? And in fact, with high masses, the sensor limit, you would interact so often in the Earth in this particular model that the dark matter actually just gets stopped. And that's, in fact, that is what happens. That if you take a dark photon model, then there is no sensor limit above sort of maybe this mass, because all this dark matter here will get stopped in the Earth and will never reach your detector. Okay. So this line that we're drawing, right, there's an assumption on this. There's an assumption that it doesn't interact with the dark photon in this particular case because it would just get stopped above these masses. But more interestingly now for this point is that at these low masses, you can see we're in a region where we expect the dark matter to interact once or a few times, and we could see a modulation. We do the same thing with a light mediator. So same kind of plot. Here's the limit, and again, I'm just drawing the one scattering line. And again, you see that at low masses, we're actually in a region where we can expect multiple scatters. And in the middle, we're sort of fine. There's not that many scatters, around 10 maybe, where the current limit is. So it's important for current experiments, especially low masses if you want to do a search. And also, so this then allows us to have a discovery opportunity for dark matter, okay? So just to take an example, so let's take, this is the sensor limit, again. This the solid line. Here's the projection of sensor at 100 gram year exposure for an experiment at Snow Lab. Let's take this point here, just below the current limit. And this is the kind of signal you would expect to see. Here's the rate of single electron events as a function of the day. And we expect this kind of modulation at Fermilab. We expect actually a huge modulation from dark matter scattering through a dark photon that produces single electron events. And in Bariloche, the rate is lower because we're on the Earth's shadow, but the modulation is actually higher because the fractional modulation is actually higher because around this region here, the dark matter scatters so often that it wouldn't even make it to the detector, and then only certain parts of the day would you actually see a signal. So the modulation itself is actually higher, even though the overall rate is a bit lower. Okay, so this is a great signal. You can look for it, and it will allow you to improve the search for low mass dark matter, which, as I already mentioned, is where you just produce a single electron event, which is lots of backgrounds, as we said, but this actually allows you to prove the signal, the search. And this is something we're doing in Sensor right now. So we do have a modulation search that's in progress. And there's also an effort in Argentina to do this in the southern hemisphere. Okay. So here's the projected limit. So here sort of is the limit that you would get just from counting how many single electrons you would get. That's the solid line. But then actually if you do a modulation search and assuming that you have the same kind of background that Sensor sees right now, you would actually improve. This is 100 gram day, 100 gram year, and 10 kilogram year. So you can really see that you get 1 or 2 orders of magnitude improvement in the search where you can see a modulation signal. So I think this is a nice little signal. Okay. Yeah. We've taken data. So originally in the limit that I keep showing, that was taken for a day-long exposure. So that's too much, but we've taken data on shorter time scales here. Okay, I can stop here. I'll just summarize very quickly. So we have 2 new detection concepts. One of them is using quantum dots. So please speak to Carlos, who's an expert on that. He's working on that with me. And also, Aaron is here at the workshop. You can talk to him if you want to know more. And we also have an idea using doped semiconductors. And then this last topic was going to be on calibrating the Migdal effect and neutrons. So as I said, we rely so much on this Migdal effect, but no one's actually ever seen this. But I think over the next 1 to 2 years, you'll have measurements on xenon and silicon in terms of looking for the Migdal effect with neutrons and really trying to calibrate this. And it won't be the last measurements because you really want to have a lot of data to calibrate sort of the entire spectrum that you can get from this. But that'll be very important to give us confidence in these limits that we get from the Migdal. Okay, that is it. Let me go to the conclusions. We can use the city touch bar, which I never use otherwise. Okay, here we go. Okay, so there's been a lot of theory and experimental progress, which I told you about, which has happened. Well, briefly told you about it. So many different detection concepts with lots of target materials, some of them quite exotic and interesting to other fields as well, like condensed matter. Lots of progress in terms of calculating scattering rate in crystals, and also a lot of experimental progress in probing these very small signals. And I think what's very important is to really understand the low energy backgrounds. We've got some progress on this, but a lot more work is needed. I think this is one of the big topics. There's actually a workshop series called the XS workshop series where people are looking at this, where all the experiments are coming together to try and understand these backgrounds, what people are seeing. And then I also talked about dynamic modulation, which I think is a nice little signal that's relevant for the current experiments. And I didn't talk about this, but you should ask Carlos for the quantum dots and also Aaron. Okay, thanks very much.